Can we?
Sure.
Okay.
Recording in progress.
Okay. It's a good pleasure to have Chao in as our speaker today. Chao is a PhD student at the University of Colorado Boulder. Although Chao is still a PhD student, I think Chao has done a lot of interesting and important works. One of the central themes of Chao's work is to study how fast the quantum information can spread in a quantum many-body system. To this end, Chao has established some very powerful generalizations of the classic Lieb-Robinson bound in systems with non-local interactions and in systems with measurements, with quantum measurements. This problem of how fast the information can spread in a quantum system is also related to some other topics, like how fast one can prepare some specific quantum states that can be used as some resources for information processing tasks. And also this topic is related to how much effects perturbations have on some quantum states. Beyond this serious work, Chao has also done many other interesting things like the characterization of quantum many-body entanglement in topological states and conformal field theories and so on. We're happy to have Chao to tell us about his new result today. Chao, please.
Thank you, Liu Jun, for this kind and detailed introduction, and thank you all for coming. So it's my great pleasure to be here, and I'd like to tell you about something about physics of matter in the so-called low-density parity-check codes. Feel free to interrupt with questions. So the so-called low-density parity-check codes, or LDPC codes for short, are a family of error correction codes that are widely used in everyday electronic devices. For example, when you use cell phones to send information, then what it really does is actually to use this LDPC code to encode the information first and then send it through some noisy channel so that after decoding, the receiver can receive the faithful information. Okay, so this is a concept born in computer science, but maybe like as suggested by the Nobel Prize, maybe it's worth investigating these concepts in physics, and this is what this talk will be about. And actually, in general, error correction kind of naturally emerges in physics. So let me first demonstrate that using a simplest example, and at the same time, I would also like to set up some notations. So let's just consider the 1 de-Ising Hamiltonian H naught, which acts on bits or qubits, and each of its local terms is basically zi plus 1. So it's kind of the parity on the 2 bits, where z is the poly z. And we know that this Hamiltonian has these 2 ground states labeled by z, which is the all 0 and all 1 states. And these are just the 2 code words of the corresponding classical repetition code. Or basically you just say, well, each term in my Hamiltonian, that is a parity check zi plus 1 for the code. And you can just write down all the parity checks in rows to make the parity check matrix of that classical code. And this analogy goes further. For example, you have this symmetry operator, the product of x's for the Hamiltonian, and that corresponds to precisely the logical operators that connect between code words. And this Ising Hamiltonian has this spontaneous symmetry breaking in physics. And what that corresponds to is kind of just saying that, well, this repetition code has error correction property that is code distance is large. So here code distance is the minimal number of bits you have to flip to map between code words. So basically for error correction code, we have these 3 parameters NKD. And for beta code, you basically want to have like by fixing n, you want to have k and d large, where d is code distance and k is the number of logical bits or logical qubits. Okay, and a general low-density parity check code is just a slight generalization of this Ising example. So here you just specify a set of parity checks C, and each C is a subset, a set of bits. And for each C, you have this basically the product of Z's. in C that measures the parity in that set. And what this low density means is that you further require that each set C contains only order 1 bits, and each bit is involved in at most order 1 checks. So this low density condition makes sure that your H0 is extensive. And you can think of this LDPC code Hamiltonian as a local interaction on some bounded degree graph. There's also an alternative way to think about it, which may be useful in some case, where you can think of it as a kind of bipartite graph, where you have this circle vertices labeling the bits, and the square vertices labeling the checks. So, and for example, this low density condition basically means that this bipartite graph called Tanner graph has bounded degree. Okay, so why do we care about LDPC codes? Well, I think maybe a main reason is that because good LDPC codes exist. So here, good means a precise statement that for such codes, D and K both scale linearly with N. So it's kind of the optimal scaling. And such good codes have to live on an expander graph, which cannot be embedded in any finite dimensions. So the detailed definition of this expander graph is not important here. It's just some graph that is kind of locally tree-like, and it also have long loops that make the graph highly connected.
Basic question. Maybe you mentioned it. What is the density here?
It's like the kind of the number of checks divided by the number of bits. So it's just a terminology. But like low density, the meaning of low density is this precise statement here. Or
So the density is the checks related to each bit.
Yes.
And in this figure, in this particular figure, what is the C?
So in the upper figure, here I just give an example where C is these 5 bits. So the bits live on the vertices of this bounded degree graph, and I claim that all the terms in H0 or C is kind of a local set on that bounded degree graph. And that corresponds to the product of these 5 Z's.
Then can I say that the condition of low density is just in the language of condensed matter saying the Hamiltonian is a field body Hamiltonian.
Yeah. And field body basically means that this first sentence here, like each C involves order 1 bits, but here I require extra condition that each bit is also involved in order 1 checks. So maybe like that's a little bit more restrictive than like K-local Hamiltonians.
I see.
So you can consider it in a bounded degree graph. Okay, so
I'm sorry, this may be a follow-up on that. So just want to make sure. So from this definition, the usual kind of surface codes, actually, they are low density.
Yeah.
But probably they're not good. But I mean, they're certainly LDPC.
Yes. Although, like in this talk, like sometimes I will use LDPC to refer to like particular expander graph. But let me try to be more clear about that. Yeah, strictly speaking, surface code belongs to LDPC. Okay, so like these are for classical LDPC codes, and you can make a similar definition for quantum LDPC codes, and just recently discovered that also good quantum LDPC codes also exist. So these codes are basically the kind of best codes in some sense that it achieves extremely robust error correction because it has large distance, and also it achieves that with only a constant overhead because you have constant encoding rate. And such codes also host like novel physics. And here, let me just mention this kind of remarkable one, which is this so-called no low energy trivial state NLTS property. It basically says that, well, we know that the ground states, the code words are entangled, but actually for some good codes, actually all the low energy states are all non-trivially entangled. So this is kind of a remarkable fact that actually quantumness can be like robust in finite temperature environments. Okay,
So when you say all the low energy states, so where do you put the cutoff to separate the high energy and low energy states?
you just put a cutoff, which is a constant times the n times the number of qubits. And the constant is maybe 0.01, but it's a constant independent of n.
Oh, you mean there's a finite density of states that
Yeah.
are not new. I see, I
Yeah.
see. Thanks. Also, just to make sure if I understand what you said before, you said each bit in O1 checks. Does this just mean that, for example, in this Hamiltonian, it just means each term has finitely many eigenvalues?
Well, each term is field body, so it should have a finite number of eigenvalues. I think that comes from the first restriction here.
Okay, then what does it mean to say each bit has O1 checks?
Yeah, because so for example, let's consider this particular bit. So I have this C here, I can have some C here, I can have some C here that involves this bit, but I don't have like very long range C's on it.
Oh, I see. So each degree of freedom is still interacting with finitely many
Yes.
things.
Mhm.
I see. Thanks.
Sure. Okay, so although to have this like NLTS good properties, you need to have the code living on an expander graph, but this kind of expander setting may become more and more relevant in real experiments. And that's because like for some of the quantum platforms, we have the ability to move qubits around, and others we can kind of engineer some hyperbolic lattices or like even engineer auto interaction. So hopefully, I have shown you that actually LDPC codes are kind of interesting and useful in physics. So for this talk, I will tell you about two stories about LDPC codes from a physics perspective, and one for classical codes and one for quantum codes. And so the first part is based on this work with Rahul and Andy at CU Boulder. And we basically did the following. So we consider a family of classical LDPC codes, and we consider generic quantum perturbation on it. Then we show that this actually provides the first provably robust example of many-body eigenstate localization. And in particular, I would like to spend some time to show that you can prove this by using two simple ideas, that is extensive energy barriers and detuning. Okay, so what is localization and why is that interesting? Well, let's first consider like a quantum many-body system that starts from, say, a product state and evolve under its own Hamiltonian dynamics. And there's a folklore saying that, well, if you consider a generic system, then the local information will get scrambled. And at long time, when you look at the local density matrices, they will look almost the same as the thermal density matrix, where the temperature, etc., are determined by the observed quantities. And it is proposed that actually the underlying mechanism for this is that actually any eigenstate of the Hamiltonian at finite temperature is just equal to the thermal state when you probe locally. And this so-called eigenstate thermalization hypothesis, ETH, is kind of a quantum version of ergodicity. And it is good because it provides a statistical description of the long-time dynamics. However, this also is bad in the sense that it does not allow for like interesting long-time dynamics. So we would like to find out, well, are there any counterexamples for ETH? And if there are, maybe we can use them to like store or process information. And there are many known ways to break ETH. For example, you can have like integrability by having many conserved quantities. You can have Hilbert space fragmentation where even in one symmetry sector of the Hilbert space, it further fragments into different Krylov subspaces that do not connect with each other. For free particles, you can have Anderson localization due to disorder, but all these three kinds of mechanisms are kind of fine-tuned because, for example, for fragmentation, as long as I perturb the system so that I connect the different subspaces, then you would expect that the eigenstates will become strongly mixing the Krylov subspaces and destroy the fragmentation. So we want something non-fine-tuned, and in particular, we want something which is really called the many-body localization. And the rough picture is that, well, even if you have the couplings between the different states, when you look at the eigenstate of this non-fine-tuned Hamiltonian, it's still localized kind of at some corner of your total Hilbert space. For example, it can have maybe like 90% support here on the L0 state, and 9% on like these states, and 0.9% these states, etc. So it's like exponentially surprised around this L0 state. So this is our hope that some systems can achieve this, and the most widely studied system is the 1D disorder spin chains, where actually dating back to Anderson, there have developed some like deep physics theories trying to argue that it has many-body localization or MBL. However, there are recent numerical simulations about this system, raising serious debate that, well, is this really a localized phase at thermodynamic limit, or it's just some finite size effect that you see in your simulation? And this debate is unresolved because currently the existing proof either relies on assumptions or this recent one that relies on extremely large disorder. So we want to ask the question that, well, are there any other systems that may have many-body localization that may be like much simpler to prove, and such that there is no debate for that system? Okay, and we find that actually some nice families of LDPC codes, classical LDPC codes, do the job. Okay, so what do I mean nice here? Well, let's consider good classical codes. Remember that good means K and D both scale linearly with N. And I require this extra property called local testability. And that is defined by this equation. Let me explain that to you. So basically, you pick any bit string X, and you ask, well, what's the distance to the set of code words Z from that X? And there's a minimal distance of that. And local testability requires that, well, this X has energy from your code Hamiltonian. That energy should be at least proportional to the minimal distance to the code words. So in other words, when you read this equation this way, then it means that all low energy states where this thing is small means the state is low error. And such good codes with local testability exist due to recent constructions. Actually, it's related to good quantum LDPC codes.
Sorry, so did you say X is a state?
X is a bit string, and it can also be viewed as a product state in the Z basis.
I see. Why is this called a local testability?
Yeah. So it's a terminology mostly from the computer science part, which basically is considering the following task. So suppose I give you a X that is either a code word or it has finite number of errors. Then you want to kind of locally only check local parts to decide which case it is. And if it has this property, then it means that, well, because it has a finite density of errors, also has a finite density of flipped checks. So you can just check some local regions and be very confident whether this X is a code word or not.
I see. Thanks.
Yeah, thanks for the question. So here, what does this local testability buy us? Well, let's consider the energy landscape of this nice classical code. So at energy 0, we know that there are exponentially many code words, and each pair of them are separated by an order n Hamming distance. And when you go up your energy a little bit, localized stability means that, well, there are no states, for example, here, because like all lower energies should be lower, so the lower energy states should be clustered around the code words, right? The red lines. And you can basically formalize this argument to say that, well, actually, by going up energy, each code word grows to an energy well. And this energy well is very deep. It has an extensive energy that is order n, and different energy wells do not touch with each other. They can only be connected by some high energy stuff. So here you can already see the intuition of why such system can host localized states, where it's just localized around one energy well and does not explore all the other wells. And that's simply because you have this, an important reason of it is that it has this very large energy barrier. So a lower energy state will be probably localized in one well. And that is basically our goal. And I should mention that actually this similar energy barriers also appear in some spin glass models. And this paper also proposes that such spin glass models may have localization. But I will say that actually this LDPC setting is kind of simpler, it's cleaner, that it does not require either frustration or long-range couplings, so that we can give a simple proof. Okay, so more precisely, I'll consider the following setting. So I have this H naught as the classical LDPC code Hamiltonian. I perturb it by two quantum perturbations, V plus HL. And this first part V is just any field body quantum Hamiltonian whose optimal norm is bounded by ipso times n. So it includes the case where V is sum over n terms, where each term is order ipso. Ipso is some small number that we will choose. The second part of the perturbation is a longitudinal field, and which we'll call it detuning. And each local field Hi, we assume it to be an independent and identically distributed Gaussian random variable. And note that I have this 1 over square root of n factor in front here, which means that, well, if you do not care about this 1 over square root of n, that small parameter change or Hamiltonian, then you can view this V plus HL as a whole, and that is a generic field body perturbation you would consider. So what we prove is that, well, for any such V, as long as ipso is smaller than some constant, say 0.1, then with overwhelming probability of choosing these detuning parameters, any eigenstate psi at low energy or at the energy density bounded by the constant C1, that state is localized in one well. That is, you give me an eigenstate psi, I give you a codeword C such that this state is mostly supported in this well, and its support outside of this energy well is exponentially small in n. So intuitively, it's basically plotted here. And this serves as a robust violation of ETH at low temperature. This theorem is about eigenstates, and as a simple corollary, this also implies that for dynamics, if you start from one well, it will never go out of that well, even for
excuse me. Yeah, maybe I missed something. So, do you have assumption on this H0?
Yeah, this H0 is this nice LDPC classical code. I did not write down the specific definition for it, but there exist such codes. So I just pick any one of it.
Okay, thank you.
Mm-hmm. Okay, so in the next few slides, I would like to sketch you how we prove this, because for the disordered spin chain story, it's like it has this serious debates. So I really want to show you actually that localization in this model is much simpler. Okay, so the proof.
Question.
Mm-hmm.
So in this picture, the bottoms of the different wells have the same energy.
Yes.
If they do not, how should I imagine it? If they do not, if they are separated by a little bit.
That does not matter because you still have this, as long as you have this like large energy barriers, extensive energy barriers. And it's just for this very nice codes, you accidentally have all the wells to have the same lowest energy.
I see. So the definition of a well is some states, some collection of states such that this energy barrier is of order n. And any collection of such state I will consider it as a well, and this state applies to all states close to these wells.
I think so.
Thanks.
Cool. So I see a chat here. Okay, so
some classical stuff. Sorry to interrupt. It's just some classical guy who was did a KTP talk about the same kind of picture. You probably already know it, so I wanted to mention it, but I didn't want to interrupt. So I interrupted. Sorry.
No worry. Maybe I can check it later.
Yeah,
I don't know that's a precise thing. Yeah. Okay, so the first step of the proof is actually like other people done for us. It's just this nice LDPC codes exist so that we have this like exponentially many deep energy wells. All right, and for the second step, I claim that when you look at this perturbed system at low energy, it is kind of governed by effective Hamiltonian H, which consists of two parts. The first part is the well Hamiltonians which act within each well. And so it's like a block diagonal terms. And there's also this H larger that connects different wells. And the claim of the second step is that because of this extensive energy barriers, actually this H larger, when it acts on low energy, is extremely small. It's even ipso to the n small. And
just to make sure, in the second step, does this form of the effective Hamiltonian hold as long as there are exponentially many deep wells? I'm asking whether you really require the starting point is the original nice LDPC code, or do you only require the exponentially many deep wells?
I don't need exponentially many wells. I need the deep wells. I need really extensive energy barriers. But if you have exponentially wells, then our result will be that, well, your state only explores an exponentially small subspace. So that just makes the final statement sounds a bit stronger.
I see. Thanks.
Okay. Let me not expand this second step. And here's this third step, which says that, well, because I have this detuning part in the Hamiltonian, it turns out that actually when you talk about the energy differences, for example, about two energy levels, one from say HC, one from HC prime, that two energy levels have a typical energy difference that is 2 to the minus n. Although it's exponentially small, it's much larger than this ipso to the n when you take ipso to be, say, 0.1. So that when you compare the last two steps, you know that like from a simple perturbation theory argument, this H larger will not mix your eigenstates. Okay, so so this proof kind of suggests that actually the localization in your model is kind of a close analogy of Anderson localization. It's just kind of Anderson localization in many body systems. Why is that? Well, we know that Anderson localization kind of relies on the fact that, well, you need this hopping strength to be much smaller than some energy difference. And that is also what happens here. And also naively, if you think the hopping strength is like this perturbation, the bare perturbation ipso times n, then it's still kind of controlled by this extensive energy barrier. And also we expect the high energy states are thermal in our model. So there's probably some morbidity edge in between. that is like Anderson localization in, say, 3 dimensions. Okay, so let me get into a bit more detail about how we prove this third step, because in some sense, maybe this is kind of remarkable that we can control this exponentially many energy wells, even for a system that we cannot solve. We cannot solve all the eigenstates. Okay, so let's just focus on trying to avoid degeneracy between the energy levels in the all zero well, that is the well corresponding to the all zero codeword, and versus the all other wells. Okay, and the idea is that, well, I have this IID Gaussian random variables HI, and you can kind of transform the random variables so that, well, you can define this H all zero, and that is basically the kind of total Z field in your HL. And you basically want to use this HCl to avoid the degeneracies. How do you do that? Well, suppose at some unlucky parameters, I have a resonance between the different energy levels, so that when I consider this H larger, this coupling between the wells, the eigenstates may be delocalized. Then what I do is just to slightly increase my H0 a little bit. And what happens is that actually the spectrum slides relatively. So the all zero well, its energy states all slide up with a very large slope, while the states of all other wells does not have that large slope. And you can convince yourself that actually this just comes from simple like Hellman-Feynman theorem, which tells you how the energy level changes when you change the Hamiltonian parameters. And the fact that you have large distance between the different wells, so that you know that states in the different wells have different Z polarizations. And finally, here I just tackled one resonance, but there are at most 2 to the 2n that many number of energy pairs. So actually, and for each pair, you only need to slide H0 by a little amount. So even if you consider all energy pairs, you can conclude that only exponentially small, with only exponentially small probability that you have a degeneracy. Otherwise, you have degeneracy much larger than epsilon to the n. And from the previous slides, you can conclude localization. Okay, so even if we write down our whole proof, it's only like 5 pages. So if you're further interested, you can check out our paper. We think that this LDPC setting is probably the kind of simplest setting for localization to happen. Okay, so before I switch gears to the second part, are there any questions? Cool. So let me start to talk about like quantum LDPC codes, and this is upcoming work with my advisor Andy. So we basically consider that let's say you have we basically prove that for many classes of quantum LDPC codes, we consider quantum perturbations on it. Actually, the ground states, the error correcting ground states are stable against generic perturbations. And in particular, I would like to spend some time on explaining like beyond we require like these are good error correcting codes, we require some properties, extra properties for this stability to hold. And I'll explain what that is. Okay, so to warm up, let's consider the simplest kind of simplest error correction code, quantum error correction code, the toric code. So as you may all know, that this Hamiltonian, torical Hamiltonian has these 2 sets of checks, where AV is the product of all x's around the vertex P, BP is the product of all z's around the vertex around the plaquette P, and this is a commuting Hamiltonian defined on the 2D torus, and this quantum stabilizer code with this code parameters. Like it encodes 2 logical qubits, and it has distance L, which is the linear system size. And for stabilizer codes, we have this stabilizer group, which is where contained of stabilizers, where each stabilizer is a product of checks. Here check is just a term in my Hamiltonian. And here, any stabilizer is just some contractible X or Z loops or product of them. On the other hand, you also have like logical operators, which are polystrings that are not in the stabilizer group, but commute with stabilizers. So here have basically 4 families of them because we have 2 logical qubits, and it is defined. You can define logical operators. If you have a logical operator, then you will multiply with stabilizers to a logical operator. But here the key is that any logical operator will be some non-contractible loop around the torus, and that makes my distance large to be linear system size. Okay, so we know that toric code has error correction properties, and people have been trying hard to realize that in experiments. So we want to know, well, is that stable against perturbations? And for example, you can add some fields and try to plot the phase diagram, and you'll see that, well, around the toric code point, there's a toric code phase, stable phase around that. And remarkably, this has been proven for generic local perturbations. And this also justifies the terminology that, well, this phase is topologically ordered. And more precisely, what is proven is that, well, starting from, let's say, a toric code Hamiltonian H0, when I add any local perturbation, originally you have 4 degenerate gap to ground states, and the gap remains to be order 1. At the same time, although the ground states do not become not exactly degenerate, they only have a very exponentially small energy splitting. So you can view this H0 plus V as an approximate error correction code, where the different codewords dephase very slowly. And moreover, you have a quasi-local unitary U that can connect between the old and new ground states.
Does this proof only apply to the toric code model or also other related models?
That's a good question. So this paper proves that all commuting finite dimensional codes with a property called local topological order has this property. And I will talk about local topological order later. And toric code satisfies this. So however, this proven theorem is limited to local perturbations. Now you can ask, well, is it stable against non-local perturbations? And perhaps more importantly, this toric code has a vanishingly small encoding rate. So, and we know that, well, so these good quantum LDPC codes have large encoding rates and large distance. So we want to know that, well, are these codes stable? If they are stable, then maybe these codes are also useful. Are more useful than you think. And there are actually previous works working on this problem. For example, there are some physical arguments about this stability, and also there's this stability is proven for some cases of quantum LDPC codes. However, for example, this the family of good quantum LDPC codes was not known to whether it is stable or not. Okay, and here are our results. We consider any field body perturbation V that has a local strength bounded by, say, 0.1. Here, local strength is that my V contains of local terms, and I just pick any given qubit and ask, well, what are the operator norms that touch that qubit? And under any such perturbation, we prove that a quantum LDPC stabilizer code is stable in distance, explained in the previous slide, and this energy splitting is exponentially small in the code distance. So if our D is a power law of n, then that would be an exponentially small splitting.
Sorry, may I ask a question?
Sure.
Yeah, It seems that the result here, you basically means that the LDPC code can be treated as some kind of stable phase of matter, and which is pretty robust under some k-local perturbations. It seems that if you consider slightly different but essentially equivalent setup, is that I think if you consider some kind of k-local quantum channel to perturb the system, according to your result, my conjecture is that there might be some finite threshold of decodability of the LDPC code. Is that right?
I think that is no, in the sense that for example, that these good quantum LDPC codes have linear distance, so that's, I think, straightforwardly implied you have a constant threshold. And on the other hand, like there is this work which suggests that there may be connections between these two concepts, but it's not sure whether you can really go through that connection like mathematically.
Oh, thank you.
So we prove the stability, but under one assumption, which we call check soundness, and for that I will explain what that is. For now, let me just say that, well, this condition is satisfied for like these families of codes, so these are stable. What are them? Well, it applies to all known families of good LDPC codes. It also applies to this so-called hypergraph product expander codes, which is not good, strictly speaking, because its distance is only sort of n, but it's still a constant rate code, and also it's a kind of much simpler construction than these really good codes.
Sorry,
May I
just
have a
a
question.
Chao, please.
Oh, okay, yes, thanks. So I want to sort of put this theorem into sort of a perspective. So if I, without proof, would people generally believe that these LDPC codes are stable, or is it that given the random looking code, you really have to check? Or, I just want to understand, is it that your theorem makes everything airtight, but people had the expectation that it should be stable, or is it that it's 50-50 or whatnot, like it's completely unknown?
Yeah, my guess is that maybe all reasonable codes are stable, but
I see.
but we only know that if you can explicitly check this property, and I will explain what the property is. So yeah.
Okay, yeah, thank you. Yeah.
Sure.
Sorry, I have one more question. Can you just remind us about the definition of good LDPC code? I think previously you said by good you mean both K and D of order of n.
Yes.
So toric code K is just the 2. So that's not good.
Yes.
So I see. So you mean the previous proof applies to systems like the toric code, and now this is a generalization to the case where even K is of order n.
So I would say the proof does not care about what K is.
Oh, your proof does not care about what K is.
Sorry?
Do you mean your proof does not care about what K is?
I think like this Bravi et al. Proof also does not care about that.
Oh, I see.
Yeah, I'll give the kind of sufficient condition for which they prove this.
So there's another general question. If we go to the next page. So in terms of for these codes, if I want to ask what are the corresponding quantum phases for matter corresponding to the good LDPC code and this hypergraph product expander code, what are they?
I don't know. I think it's open questions like, I even don't know like whether like, for example, the different families of good LDPC codes are in one phase or they are different phases.
I see. And also it's not known what's the effective field theory for them.
Sure. Yeah, I think that's completely open.
Thanks.
Okay, so some implications of our theorem. So as suggested by this previous work, we proved that, well, these constant rate codes are stable, so they represent the phase of matter that actually violates the third law of thermodynamics. Because in the ground state subspace, you robustly have this exponentially many deterrences or extensive entropy. So that's interesting point of view. And second, because as suggested previously, toric code is an LDPC code, strictly speaking. So our proof also implies that, well, toric code is stable against especially non-local perturbations. Because here for V, I don't require it to be local, geometrically local. Third, we adapted our proof to prove that actually some classical LDPC codes under some condition according to this taxonomies is stable against symmetric perturbation. So this is like, well, we know that Ising Hamiltonian is stable against X perturbations, but not against Z perturbations, and X is symmetric. So here is a generalized version of that story. And a technical improvement is that we also have some stronger locality bounds on this quasi-local unitary U, and that has some actually qualitative predictions that we will report in other work. Okay, so in the rest of my talk, I have to talk about this taxonomies. And let me start with this question, like, suppose I know quantum code has air property, is that sufficient for stability? In the sense of this previous, like, gap does not close, etc. Sense. And because there may be some folklore saying that, well, in finite dimensions, when we talk about topological error correction codes that are topological order, and we know topological order are stable. So is that really true? Well, there are some like good physical reasons for that, because, well, error correction implies that the ground states are locally indistinguishable, and that favors stability because, well, if I have this local perturbation V, and if I just consider first order perturbation, then I know that this V cannot induce the energy splittings among the degenerate ground states, because in this ground state subspace, labeled by this projector P, I know that PVP is an identity. Are there any questions? Okay, this argument also holds for higher orders. So here, by higher order perturbation theory, this can be formalized by the so-called Schrieffer-Wolff transformations, and that is kind of the technique we use to prove our results. But for this talk, let me just say, well, you can imagine there is some like higher order perturbation theory, and at order K, you basically are treating some operator looks like this, like V1, V2 times Vk. And here, each Vi is a local term of your original perturbation. Okay, at higher order K, you can still have this argument that, well, this operator acts as identity in your ground state subspace, so it still cannot induce energy splitting as long as your K is smaller than the linear substance size. Because before that order, each Vi is local, so it cannot form a logical operator. Well, on the other hand, after you get that high order, although there are some remaining perturbations that could cause splitting, well, you can imagine that it's exponentially small in the perturbation order. So what have been written down in this slide kind of favors that tells you that, well, error correction is important for stability. However, it turns out that itself is not sufficient. Why? Because here I'm basically only considering the energy splitting property, but I also want the gap should not be destroyed when I consider the perturbation, and maybe that's even more important. Like it's the first thing you want to check. And for that, actually, it turns out that for some error correction codes, actually, even your V is some over stabilizers that can destroy the gap. Okay, let me just give you the simplest example. Let's consider a Ising version of the toric code. So this Ising toric code consists of like all the AV checks of the original toric code. But for the Z checks, I just pick a particular plaquette P0, say here, and that BP0 appears as check for this ice inversion. But for all the other Z checks, I just consider like BP, BP prime, where P and P prime are neighboring plaquettes. So observe that this icing toric code has the same ground states as the original toric code. So it actually has exactly the same error correction code. But this icing toric code is unstable when you consider this perturbation V, which is sum over BP. And why is that? Because, well, for X0, you have this like your ground state is BP equals to +1, but you also have this BP equal to -1 subspace. It's only constant energy higher because you only violated this single check. And when you turn on this perturbation, well, that makes this -1 ground state, -1 state as the new ground state immediately. Okay, so error correction is not sufficient for stability. And people have come up with a notion called local topological order to be really a generalization of the error correction condition that is sufficient for stability. And it has some radius r. And I define B bar to be B plus its neighborhood. And local topological order, or LTO, requires that, well, for any ball with radius smaller than in B. So what are these local ground states? Well, you just drop all the terms in H0 that, and you can convince yourself that this condition is stronger than the error correction condition. And it reduces to that when you take B bar in this equation to be the whole system. And also observe that, well, this immediately rules out the unstable icing toric code because suppose my P0 is here and my B are far from it, then this PB bar actually contains like two sectors, two subspaces where BP equals to +1 and BP equals to -1, and these two subspaces are distinguishable locally. And it to be, I require it to be expandable to a product of checks in B bar, because if that holds, then we know that every check acting on this PB bar is 1. So this OB is just 1, or identity. Okay, so LTO is like the condition people use for stability in finite dimensions, and we basically want to generalize that to quantum LDPC codes or expander graph settings. And however, this generalization is not straightforward. First, sorry, so let me check. So how many time do I have left?
I don't really want to put any constraint. You can take
cool.
as much as you want.
Cool. So nice. Well, remember that, well, this LTO in finite dimensions care about small regions. But this is not to consider origins for, say, expander graphs, because, well, expander graph will just, its total diameter is just log n. So you can only consider balls with radius bounded by, say, log n. Here L is kind of the linear system size. So why is that not good? Well, because we know that at perturbation order larger than log n, there already exists some perturbation of this form that does not fit in any ball, so that you cannot control this perturbation already at this order, which means that finally you can only get energy splitting that is, say, 1 over quasi-polynomial in n instead of some exponentially small splitting. So this suggests that, well, why not go beyond ball regions and consider general regions? And does LTO hold for any region as long as its volume is bounded by, say, the codistance? However, that also is not true just for the toric code, because, well, just consider this loop stabilizer, which can be viewed as supported on this annulus region as the blue region. And LTO requires that this stabilizer can be expanded as checks near this region, but it cannot. It can only be expanded in checks that kind of fills the whole of this region S. So that means LTO is not quite easy to generalize, and that suggests that we actually have to fill the holes in some infinite dimensional space. Well, that seems a daunting task because like it's hard to imagine these high dimensional geometries. So instead, we want something that's more algebraic. So here is what we use. Basically, remember that LTO requires that, well, for any stabilizer, it can expand it to a kind of a small number of checks. And that is precisely used here. So I define the code to have checks on this with function f if for each weight x stabilizer, it can be expanded as a product of smaller than fx checks. Note that for each stabilizer, it can have different forms of expansions. And here I just kind of care about the minimal expansion. And also, I only require this to hold as long as x is smaller than, say, the codistance. But this is not super important here.
Sorry, what is the weight?
The number of qubits that this stabilizer acts on.
I see. Thanks.
Okay, so some examples for toric code. We have a quadratic checks on this. That's just because like this previous plot that I have this loop stabilizer and it can always be expanded into the kind of into the volume of the that the loop surrounds. And more generally, if you have local topological order in d dimensions, that implies x to the d checks on this. And what's the best case we're going to hope for? Well, is linear checks on this. Why? Because of the LDPC condition that's that the stabilizer itself acts on many bits, so that cannot be expanded to a few checks. And intricately, in this linear checks on this is kind of equivalent to the notion localized testability. If you recall, like I also have this like in the first part of my talk. More precisely, it's equivalent to local testability of the corresponding classical LDPC code of the quantum code. So let me not go into the details like how this correspondence goes. Let me just explain like morally why these two are kind of equivalent. So recall that local testability means that, well, all low energy states are low error states. And that can be viewed as a map from checks to bits, right? Because it basically says that, well, if a state violates a small number of checks, then it should be obtainable from flipping a small number of bits. And this checksum is kind of just the other way around. It's like, well, if I demand a stabilizer to act on a small number of bits, then can it be expanded to a small number of checks? So, so local testability is really a very important property in like code theory, and because of this equivalence, we believe that actually this checksumness is actually a natural property one should think about in studying or finding quantum codes. And in particular, we furthermore show that actually this technique is just useful because it is a sufficient condition for stability. More precisely, we desire this checksumness with a sufficiently slowly growing f, that will be sufficient. Specifically, if your quantum code has better than quadratic checksumness, or its fx grows slower than quadratic, then we can prove the stability for that code. If you restrict your code to be infinite dimensions, then any polynomial fx would suffice. So like local topological order is also included in our proof. And it turns out that, well, all known families of good LDPC codes and this graphical expander codes, they all have the best possible linear checksumness. So we prove that they have stability. And in the rest of my talk, let me explain like why the intuition why checksumness is sufficient for stability. Well, first observe that the unstable asymptotic does not have checksumness. Or in other words, if we require it to have checksumness, it needs to have a function f that depends on or grows with system size n. Because when you expand this stabilizer, it should be expanded as a kind of string of checks. Well, if your code has checksumness, then let's just consider maybe a simplified setting where my perturbation V is just the sum of local stabilizers. And the intuition is that, well, checksumness basically means there's a one-to-a-few mapping between these two parts of our Hamiltonian. And why is that important? Well, suppose I want to kind of figure out, well, is there a state, excited states in H0 that kind of gain or lower its energy by V such that it may destroy the gap? Well, it cannot happen for checksumness case because, well, suppose it gain energy E from violating some stabilizers so that it lowers energy by V. But because, well, when you violate one stabilizer, you have to also violate at least one check in the expansion of that stabilizer. And because you have this one-to-a-few mapping, that means that, well, at the same time, you have to also violate many checks so that actually this state itself is actually a very high energy state of H0. So you have this energy penalty that always wins over the energy gain from the perturbation. And that makes the gap is stable. And basically, this is a property that we use to kind of perform this like high order perturbation theories, and ultimately we can show the stability. Okay, so I think I'm a bit out of time, so let me just conclude here. So in the first part, I show you how to break a Gaudicity using energy barriers. And in particular, we show that, well, these classical LDPC codes form robust many-body localized spaces. So natural question is, well, can it be generalized to finite dimensions? Well, first of all, in finite dimensions, you don't have extensive energy barriers anymore. But maybe, well, can you use some like long-range interactions? Well, extensive energy barrier does not hold for like local models in finite dimensions, but maybe you can try to add long-range interactions. And also, well, you can, like I have talked about breaking a Gaudicity for eigenstates, but maybe you are satisfied as long as you have a Gaudicity breaking out to some long time scales. And that is possible in finite dimensional local models. And we have some first, we have tried develop some we have tried to develop some theory for this quantum metastability problems. In the second part, we proved that, well, many quantum LDPC codes with checksumness represent stable correcting physics of matter. And as suggested by Liu Jun, maybe it's interesting to ask, well, can we further generalize this finite dimensional physics to this LDPC setting? Well, can we actually classify these phases? And also, like, we prove stability for ground states, but you can, like, if there's like similar stability holds for excited states, and know that this is precisely what we achieved for the classic mode.
And then we rewrite your like protocol in Python. So, but I have two versions of it. The first version, the measurement produce the chaos. I write as a nonlinear. I think it was an accident.
Thanks. Yeah, so like if we can prove like similar stability for excited states, then that may tell us that actually these LDPC codes are stable quantum memories. And furthermore, there's this like NLTS no low energy trivial state property for quantum codes, but maybe you can further generalize it to say that actually quantum is infinite temperature like you can have like really true quantumness in finite temperature, and that is related to the so-called quantum PCP conjecture in complexity theory. So with that, let me stop here, and thanks for your listening.
Yeah, thanks for the nice talk. Very impressive work. Any questions from the audience?
Okay, first.
Yeah, there was these papers, by the way, very cool result. Congratulations. And there was these papers, like one by probably Hastings and Friedman, mapping chain complexes of arbitrary codes to geometrically local codes in like 10 or 11 dimensions. I think there was another paper that tried to do this recently. Have you looked into that as it relates to phases of matter?
No. So is that the link you have in the chat?
No,
or...
that's not the link. The link I had was
So-
from a KATP
Yeah.
talk 21 years ago that talked about these wells that you posted. Like the figure's like exactly the same. Hey, congrats
Hey.
again. Awesome
Thanks,
stuff. Yeah, so you might want to check that if you haven't seen it. The classical LDPC people have been onto these wells for a while. But this is like embedding non-geometrically local chain complexes into like geometrically local chain complexes in higher dimensions.
Yeah,
I think there's at least two
that.
papers. Okay.
I see, yes. Yeah, that sounds really cool.
I can send you the papers.
Thanks.
Other questions?
Oh, okay, maybe my turn. So, could you please go back to the definition of checksoundness?
Sure.
Yeah, so I'm a bit confused. So do LTO have different checksumness with from the original topological order?
So here we show that if you have LTO, then that implies checksumness with this x to the d function.
Yeah, so for two-dimensional toric code, it is still x squared, right? So why do you need the local topological order here? I'm a bit confused.
Sorry, maybe I don't get the complete question. So
why not the so by saying local topological order, you I think you're introducing a subregion, right? And you just use this subregion as your code. Then why not since I mean, why not the original, the whole topological system?
Yeah,
because
because
yeah, please go ahead.
Yeah, if you do not use this local topological order condition, then if you just use the global topological order condition, then that is not sufficient for proving stability because of this like counter example, like this Ising toric code example. Does that answer your question?
Okay, so they have the same checks on this if the topological system is the pure topological order. Then if you have some, for example, defects and maybe some local differences, then they will have different checks on this. Is it correct?
Defects. Sorry, can you repeat your last sentence?
Yeah, I mean, so you introduced the Ising version of toric code, and this version have different checks on this. You said that, right?
Yeah,
and so the introduction of the local topological order is to exclude these kind of versions, right?
Exactly.
I see. I see. Now I understand. Thank you very much. And another question is that do these results applied also to other topological orders? For example, the toric code can be generalized to the quantum Debye model, which can produce other kind of topological orders. So do these results still apply?
Yeah, I think like here I'm focusing on the stabilizer codes, but at least for finite dimensions, people know that at any commuting projectile Hamiltonians as long as they satisfy, well, then they are stable. I think
I see.
Yeah, I think for all the constructions of quantum doubles, they
Yeah.
satisfy RTO.
Okay, I think so. Yeah, thank you very much.
Thanks.
Any other questions?
Can you say something a little bit more on the last point on your last slide?
The quantum PCP
Yeah,
thing?
that's right.
Yeah, so what does our results say about quantum PCP? So what is quantum PCP? So my understanding is that, well, for example, for the good quantum LDPC code, it has this NLTS property that all low energy states are highly entangled. But for quantum PCP, you want something stronger. You want to say that, well, these states are kind of quantum in any sense. That is not satisfied by good quantum LDPC codes because these are still stabilizer codes. So, and stabilizer codes, you can compute, say, like polystring expectations. And so you basically want to say that, well, for example, you want to say, is there a model that is all low energy states are on the one hand is entangled, on the other hand is not stabilizer state, right? That's something which is still weaker than quantum PCP, but maybe that's something next you can look for. And what our theorem kind of suggests is that actually you cannot achieve that by just perturbing good quantum LDPC code. Well, when you perturb that, certainly your ground states can be like no longer look like stabilizers, but you still kind of have a classical description of that state because like we also proved that there is this quasi-local unitary U. We also have this quasi-local unitary U that's connecting these two parts. So these states are kind of, although they are not stabilizer states, they're kind of almost stabilizer states because they are connected by some local unitary. So in that sense, like you have to do something more violent to really have like more constant PCP like Hamiltonian, not by just perturbing quantum good quantum classic code. And beyond that, I don't have anything else to say about quantum PCP because yeah.
So can I also briefly understand this thing as like doing perturbations will not give you magic?
Sure, in some sense, yes.
Okay.
Okay, any other questions? Okay, if not, I think we can end here. Chao, thanks for the very nice talk, and also congratulations on these impressive works. Thanks. Bye. I will stop recording and end here.
Recording stopped.
Bye.
See you.